My name is Markus Kunene. I'm professor for sustainable metal building envelopes at RWTH Aachen University. This module is concentrating on new design rules of innovative liner tray wall systems, which are thin-walled components of lightweight metal constructions and are used as the inner layer of a double shell wall system. Liner trays are typically used for inner sheets of wall systems, but can also be used for roof lower sheets. Mostly, a trapezoidal profile or corrugated profile is used as outer cladding. Liner trays belong to the cold-formed steel profiles and are composed of a wide flange, two webs and two narrow flanges. The narrow flanges of the liner trays should be holded by attached profiled steel sheeting, since the load-bearing capacity of the system is strongly dependent on the stabilization of the narrow flanges. That is why the distance of the fixing between inner and outer cladding is important for the stabilization of the wall system. To reduce local buckling and to raise the stiffness of the profiles, the flat surfaces are reinforced with beads. Typically, the dimensions of liner trays are 500 to 600 mm wide and 90 to 240 mm high. Liner tray profiles are widely used as part of exterior wall systems for hall-like buildings in industrial and commercial construction. Due to increasing demands on the energy efficiency of buildings, various liner tray wall systems have been developed to reduce the huge thermal bridging effect of liner tray webs. The conventional solution has a directly fixed trapezoidal profile as outer cladding. One new solution is to install distance profiles between the outer cladding and the liner tray. In this case, the gap can be additionally insulated and any profile or sheeting can be selected as external cladding. The fixing distance of liner tray wall systems between the outer cladding and the narrow flange is regulated by the value S1. Depending on the construction, the length of S1 can vary. For example, when using distance profiles, the distance of the connection can be chosen larger because it is independent of the profile geometry. Due to the fact that the construction is significantly stabilized via the stiffness of the outer cladding, the fixing distance is important for load-bearing capacity. At the fixing points of the almost shear-resistant outer cladding, the narrow flanges are stabilized against lateral buckling. The greater the distance between the fixings, the smaller the supporting effect. The lateral support of the narrow flanges is important if they are under pressure. This applies especially to wind pressure in the field and wind suction at the intermediate support. The load-bearing capacity of liner trays is usually determined by tests according to EN 1993 Part 1.3 based on DIN 18807 Part 2. If no corresponding test results are available, the determination of the load-bearing capacity may also be calculated according to EN 1993 Part 1.3 Chapter 10.2. Firstly, the EN 1993 Part 1.3 gives the application range of the actual design method to calculate the load-bearing capacity. In addition to the geometrical properties like thickness, height and width, also the fixing distance S1 between the outer cladding and the narrow flange is limited. Currently, the fixing distance in this standard is limited to 1000 mm. especially the new solutions of liner tray walled systems, often no longer meet this limit. The design procedure to calculate the load-bearing capacity of liner trays distinguishes between tension and compression in the wide flange. Only if tension is in the wide flange and the narrow flanges are under pressure, the fixing distance is relevant for the determination of the load-bearing capacity of liner trays and the possible reduction of the moment resistance. The design procedure for the ultimate bending moment when tension is in the wide flange is divided into 4 steps. Firstly, the centroid of the whole cross-section is calculated. This means that the entire surface of the web and the flanges is taken into account in the calculation. Secondly, the effective width of the wide flange can be calculated on the basis of the possible flange curling. In addition, it must be checked whether shear lag must be taken into account. In both cases, the wide flange must be reduced to an effective width due to the deflection to the centroid. Thirdly, the effective areas of all compression elements must be calculated. This includes on the one hand the narrow flanges and on the other hand the web. The narrow flanges are totally pressed and the effective width of the narrow flanges considers the reductions of local buckling and distortional buckling. The web surfaces are reduced by the stress ratio psi using the effective width of the flanges but the gross areas of the webs. Finally, in the 4th step, the centroid with the effective cross-section must be recalculated. Then the effective section modulus can be calculated to determine the moment resistance. According to EN 1993, part 1.3, the influence of the lateral support of the narrow flanges is taken into account by the coefficient beta B, which depends linearly on the fixing distance as 1. This is based on the assumption that the narrow flanges under pressure are completely supported if the fixing distance as 1 is equal to 300 mm and therefore lateral evasion is prevented. This is taken into account by the factor beta B equal to 1. A fixing distance between 300 and 1000 mm results in a correlation factor beta B with a value under 1.0 and reduces the ultimate bending moment due to the reduced stiffness. However, depending on the outer cladding, the fixing distance as 1 can vary between 210 and 2000 mm. So, there is currently no valid calculation method for the fixing distance between 1000 and 2000 mm. In order to extend the current procedure, comprehensive tests were carried out within the framework of the research project GRISPE with regard to the influence of the fixing distance. Based on the test results, GRISPE provides a calculation method for larger fixing distances. Within the GRISPE research project, the load-bearing capacity of liner trays was experimentally investigated by varying the distance as 1. The load-bearing capacity of liner trays is usually determined by tests according to EN 1993, part 1.3. Reference is made to the National Annex to DIN 18807, part 2, as well as the supplementary test principles for liner tray profiles. For the determination of the characteristic values of the mid-span moment resistance, single-span tests for load case gravity loading were performed. Furthermore, instead of extensive investigations for the intermediate support area of continuous beams, internal support tests for the load case uplift loading have been carried out. The single-span tests were carried out on 2 liner tray geometries with web heights 110 and 160 mm and 2 nominal thicknesses 0.75 and 1 mm. The width of the profiles was 600 mm. As a directly attached outer cladding, a trapezoidal profile 35 to 207 mm with a nominal thickness of 0.75 mm was used. The test specimens consist of one complete and two half liner trays. The trapezoidal profiles were fixed to the upper flanges of the liner trays with self-drilling screws at a distance of S1. The length of all liner tray specimens was 6,400 mm. The overhang of each liner tray was 200 mm. The load was introduced into the trapezoidal outer sheet via transverse steel sections and timber blocks. Transverse ties prevented the profiles from spreading. At the end supports, timber blocks were used to avoid local deformation. The deflections were measured continuously in mid-span by 3 tripwire displacement sensors. The deflections were measured under the bottom flanges. The load was applied deflection controlled with a speed of 20 mm per minute. The load was measured continuously using a load cell with a maximum capacity of 50 kN. The detailed test program is shown in the following table. The liner trays of the single-span tests for load case gravity loading had a span of 6,000 mm. The liner trays of the internal support test for load case uplift loading had a span of 2,000 mm. All tests were carried out for the fixing distances 621, 1242 and 1863 mm as maximum reference without fixation so that the upper flanges were not stabilized. In all single-span tests, a non-linear load deflection behavior appeared until the failure load was reached. Failure occurred by local buckling of the upper flange in the span between the fixation of the upper flange. With larger distances between fasteners and higher webs, lateral buckling of the webs and upper flanges occurred instead of the local deformation. The test results were statistically evaluated according to EN 1993 Part 1.3 and the characteristic span moment resistance under gravity loading was determined. The diagram shows the ratio of the characteristic span moment for the 4 types of liner trays and the reference value of the characteristic span moment resistance at S1 equal to 621 mm as a function of the fixing distance S1. The reduction of the bending load capacity can be described as a function of the fixing distance and the slenderness of the webs and the upper flanges. The larger the fixing distance and the higher the slenderness of the compression elements of the cross-section, the lower the bending moment resistance. In summary, the reduction of the bending moment resistance with a larger fixing distance S1 can be explained by the fact that a larger fixing distance S1 causes a weaker lateral support of the upper flange and thus an earlier laterally moving of the compression elements of the cross-section. The actual design method is rather conservative and does not offer any solution for larger fixing distances, which is becoming more and more relevant in current practice. Especially when using distance profiles, a maximum fixing distance of 1000 mm is no longer sufficient. Therefore, the GRISPR research project investigates the influence of the fixing distance on the bending moment in order to improve the reduction coefficient and expand the application range. The result is a new calculation method for beta B as a function of the fixing distance. The new design method is based on various principles and considerations. First of all, the ultimate positive bending moment of the liner trays is generally limited by the ultimate compression force of the narrow flanges. Because of that, the compressed flanges must be stabilized against lateral buckling by the fixations between liner tray and outer cladding. So the fixing distance S1 can be assumed as the buckling length of the compressed flange and therefore the ultimate compression force of the narrow flanges and in consequence also the ultimate bending moment. The method is based on the assumption that the ultimate bending moment is approximately proportional to the compression resistance of the upper flanges. This means that the reduction coefficient beta B to respect the fixing distance S1 corresponds approximately to the reduction of the compression resistance of the upper flanges. The proposed change is to calculate the new beta B as a quotient of two compression forces multiplied by a known ultimate bending moment. The known ultimate positive bending moment is a result of testing or calculations according to the Eurocode. The method distinguishes between two fixing distances. The fixing distance S11 of a known distance below 1000 mm and a fixing distance S12 of an unknown distance between 1000 and 2000 mm, which can't be calculated with the actual design method. The compression force of the unknown fixing distance divided by the compression force of the known fixing distance is the new correlation factor beta B. Finally, the unknown ultimate bending moment is the product of the known ultimate bending moment and the factor beta B. The calculation of the new correlation factor beta B using the compression forces is divided into 4 steps. As first step, the gross cross sections of the compressed flanges have to be calculated. For the determination of the gross cross section are the flanges and the edge stiffener fully applied. In contrast, only 1/5 of the web is taken into account. The gross cross-section must be calculated separately for both flanges, because the left and the right flange are not totally equal. Therefore, the compression forces are also not totally equal. As second step, the determination of the effective cross-section of the upper flanges must be taken into account. Therefore, the width of the upper flange and the thickness of the edge stiffener are reduced as a result of local buckling and distortional buckling. This reducing method is corresponding to the actual design method for the ultimate positive bending moment in the Eurocode. So, the considered spring stiffness Kr of the edge stiffener can be calculated as shown in the figure according to the Eurocode. Thirdly, the ultimate compression force of the narrow flange with respect to lateral buckling must be calculated. The compressed flanges are considered as an elastically bedded beam under compression with respect to a lateral buckling. The fixing distance S1 is used as the buckling length as it can be seen in the figure. The spring stiffness Kfz can also be calculated according to Eurocode 3. The equation is based on a symmetric section in compression. After calculating the spring stiffness, the critical axial load can be calculated separately once more for both flanges. The characteristic compression forces for the fixing distances S11 and S12 can be calculated separately for both upper flanges according to the Eurocode 3, assuming buckling curve A0 and performing iteration. The calculations according to step 2 and step 3 have to be done for both flanges and for both fixing distances S11 and S1 too. Finally, the factor beta B is the sum of both ultimate compression forces of the fixing distance S1 2 divided by the sum of both ultimate compression forces of the fixing distance S1 1. Together with the ultimate bending moment of the fixing distance S1 1, the new bending moment of a fixing distance between 1000 and 2000 mm can be calculated. Summarizing, conventional liner trace systems with separation strip do not fulfill the actual energy and architectural requirements. That's why new solutions are developed for which no calculation methods are available in current regulations or application boundaries of existing methods are exceeded. Within the scope of GRISPR, extensive experimental investigations have been performed on liner trace for fixing distances which are normatively not or insufficiently covered. A new calculation method has been derived based on design methods from Eurocode 3 in order to extend the current application range. Thank you very much for your attention.